Need to.
All right, our meeting is started. March 23, 3 p.m. Pacific. Thanks to TeamOz for giving us something to talk about today. And once Brian and Lachlan showed up, others did as well. So there are our main show and tell today. Other things, just a reminder, next week, Gavin comes back. It's been a year since we talked to him, and he's going to have his, I don't know if he has his updated trainer or his book progress, but he's always interesting to follow. And this guy is real. I looked at his midterm. Wow, it was tough. I mean, he had these students writing legitimate big spin programs that require multi-core. So it'll be fun to hear from him. We released 2.7.0 beta yesterday, and I have a little video on that. It's 2 minutes from Jeff. Let's just watch it while people kind of load up. Let me know if the sound is not good enough.
Hello, Propeller fans. These are some of the
Does that work?
changes of Propeller Tool version 2.7.0 beta. One of the most exciting changes
Just to verify, do you hear the audio?
Yes.
Okay, perfect.
Yes.
is the inclusion of bidirectional debugging, as demonstrated by this program, Debug Mouse and Keyboard. In this example, in a loop, two debug statements use two new commands, PC mouse and PC key, to request mouse and keyboard metrics from the computer. In this case, the plot window. When the PC sends data, the code performs some action with those values. Here's an example. Over here in the plot window, I can press and hold the left mouse button while I move the mouse around to draw on the screen. I could also use the mouse wheel to change the color of the next dots that are drawn. I can press the keyboard
Don't press the keyboard, Jeff.
Buffer.
Yeah, that's probably on my end.
That's looking great.
And depending on the sharing he has, I will just copy this into the chat. And maybe you can all get to it that way. Okay, so I put a link to that in the chat. I don't know how he has it set up. It looks like when the video went into a high res mode, things stalled. So we'll try one more time.
There's some of the changes of Propeller Tool version 2.7.0 beta. One of the most exciting changes is the inclusion of bidirectional debugging, as demonstrated by this program, Debug Mouse and Keyboard. In this example, in a loop, two debug statements use two new commands, PC mouse and PC key, to request mouse and keyboard metrics from the computer. In this case, the plot window. When the PC sends data, the code performs some action with those values. Here's an example. Over here in the plot window, I can press and hold the left mouse button while I move the mouse around to draw on the screen. I could also use the mouse wheel to change the color of the next dots that are drawn. I can press the keyboard and it will plop down the keyboard code. In that case, that was the space key. Here is the A and B and C keys. There's a wide range of new functionality that can be achieved using the debugging tools with the Propeller 2 this way. The other major enhancement is syntax highlighting support for the Propeller 2's extensive list of math and logic operators. These operators can be used inside of debug statements in both spin and assembly code. What you're looking at here is a nonsense example that I wrote just to test syntax highlighting, and you can see that there's no highlighting happening here for these operators, which makes it difficult to tell that they're actually syntactically correct. So with this change, we've gone from code that looks like this to code that looks like this. You could read more about other changes made in this version by checking out the enhancements and fixes list on the product download page. Be sure to also follow the upgrade instructions to update your examples folder.
Okay.
Hello, Propeller fans.
Thanks, Jeff. Virtual Jeff. So if you download it, Jeff said he was having a little bit of crashing on his own computer, but it's the development machine and he has loads of USB drivers loaded on there. So he doesn't really know if it was his problem or not. So we called it a beta. And Chip's going to talk more about the debugging stuff. So pause on that. So Terry's going to show first what he's been doing with this LED display. He's been working 3 months, every single night. So we'll look at that. And then we will jump over to the main topic, which is from TeamOz. And then after that, we're going to look at an 8-minute video that Stephen just recorded. So Stephen's been advancing Chip's driver for the BLDC motors, and he's got a complete robot thing here, and he's hooked up a FlySky controller with Johnny Mac's driver. So we'll see that. And then Chip's going to talk about debugging at the end in Peanut. Yep. And then of course, thanks for buying the junk off my desk today. Just one big arm sweep produced 100 boxes of things. So that's all done. And let's start with TeamOz then. Brian, do you copy?
Yep, I've got you.
All right. You could share whatever you want.
Okay. Can you see my camera? Okay, the view.
Beautifully.
Okay.
Oh, wait a minute. Before you go, let's do, sorry, I want to do Terry first, if that's okay.
Yep, fine.
Okay, so Terry will be like 10 minutes. Terry, you ready?
Yeah.
Okay.
Yeah, let me see if I can share screen 2. And I guess I hit the share button. Let me know if you can see that.
Got it.
Looking
Okay.
good.
Great. Okay, so I'm going to go through this slide deck, and it's PowerPoint. I hope it doesn't make everyone too stupid. And I'll go through just an explanation of what I'm doing here, and then I'll show you some of the videos and things. Yeah, I'm really interested in using the P2 to drive large numbers of pixels. The little NeoPixels, you know, they're available at Parallax. You see them everywhere. They're almost ubiquitous at this point. And whenever you get into really large displays, it gets very difficult to, you know, program your microcontroller to handle all of the different nuances of generating what you want displayed. And so typically in the larger displays, you use some type of control software to do that. And that control software uses a protocol called E1.31. It's an ANSI standard that I believe the Entertainment Technology Association come up with. And so typically what you do is you have a PC that generates all of your images and the text and things that you want to appear on the display using software. The software that I'm using for most of this is called Jinx, and it's a free piece of software that's available. And it sends those Ether131 Ethernet packets out to the P2. Inside of the P2 configuration I have, I'm using a WizNet 6100 Ethernet controller to decode that data, and it picks up those UDP packets, sorts through them, looking for the pixel data, and let's see here. Yep, I have a dedicated cog to do that, and down here you can see. This is my rig. This is my first test rig that we had here, driving just, I believe this is 50 pixels or so. And so I have a dedicated cog that reads that data in from the WizNet. And all it does is sit there and looks to see if there's information available in the buffer, reads it in, and attempts to parse that data. I have 3 other cogs that are configured. What they do is they read the information that's been put into the pixel buffer by the first cog and pushes that data out to the pixels. I did a modification of John McPhail's pixel driver. And so his original code was set up to just drive 1 pin. And what I did is I kind of flipped that on its head and use the loop there where it's driving a single pin to where it actually drives a full byte output and does 8 pins together. So well, with 3 cogs, you can drive 24 pins with that data. The WS2811 and 2812 data is, it's interesting the way the packets are structured for that, the way the data is sent out to them, because it's not based on a high level or low level to send the ones and zeros. It's based on the amount of time that the level is high or low determines if it's a 1 or a 0 that goes out to the pixels. And so it gets somewhat very time constrained trying to make that work. We could probably run many more pixels than what I've done. This is just how far I've gotten it to go so far. And at some point, I'll go through and optimize and see what all we can do with it. Something to tell you a little bit about the way the E131 packets are structured and everything. So there is an industrial light control protocol called DMX 512. And the same Entertainment Association, Technology Association also produced that standard. And so what the E131 is actually encapsulating DMX universes. And so with a DMX universe, you can only have 512 bytes of data, and that limits you to 170 pixels per universe because you have a red, green, and blue. So logically, you're grouping these things together in groups of 170 pixels or less whenever you're setting this up. You have to do your mappings in the software on the PC as well as on the P2, and I've created a data structure that allows that to happen so that you can say, okay, this universe goes to this pin, and the next universe also goes to that pin, but it's the first available pixel after the universe that's already in there, and so on. I don't have a good user interface yet to be able to do those mappings on the P2, but that's coming up next. Those are the next things that we're doing here. And so yeah, that's where you can map multiple DMX universes in here. The way this display is done, you have a full universe. It goes this way across the matrix and then does a hairpin turn and comes back the other way. And so this is 24 pixels tall by 50 wide. So it's 100 pixels that are within that DMX universe. And the mapping of that is all handled in the software. The nice thing about it is the direction that things go doesn't really matter as long as you map it correctly in the PC software. It makes it easy. Let's see here. Move on to the next slide. This is a little bit of technical detail about the performance of this thing. So this is an interrupt that I have configured on the W6100. And whenever there's data available, this interrupt goes low. And so what I'm able to do is use this sort of as a canary in a coal mine to determine if I have data available and see if I'm getting the data out quickly. The P2, actually, I'm doing no interrupts on the P2 or anything like that. I'm just continuously polling it because I have a dedicated cog for it. This is just a way to visualize, do I have data available? And these are completely full DMX universes here. And so you can get, basically 1,024 bytes within, less than a millisecond out of it. With this right here, I'm showing the Ethernet interrupt, and this is the data that's going out via the pixels. And something to note here, these are somewhat smaller, and that's because I look for only the data that it needs out of that packet. So it identifies, okay, which universe does this belong to? Okay, I know what that is. And based on the configuration in that data structure that I talked about, it knows how many pixels to read. And so it only reads the amount of pixels that it needs, and then it marks the packet as received and continues on and looks to see if it has another packet available. If you'll notice, these right here are very, very small. Whenever it says it had data available, that's because there was no configuration to be able to deal with these. And so it just skipped right over it and said, okay, I don't need to read those, go back and go to the well again and start looking for data again. Something to note is the W6100 at 100 megabits a second cannot do this. You have to set it to 10 megabits a second. At 100 megabits a second, it basically does not have enough turnaround time to be able to get the data out of the small buffers that are in that chip. So if you've ever worked with the 5100 or in this case, the 6100, that's probably going to be true of both of these, that yes, it can do 100 megabits a second. You're not going to be able to do that with UDP. It's just the performance isn't going to be there because the chip's just not fast enough to do it. With this project, I got the P2 clocked at 270 megahertz. The reason I did that is because that's what it defaulted to for the HDMI display. It's like, okay, that's fine. We'll go with that. That seems to be stable, so we'll run along with that. And also, yeah, so I have the WS2811 outputs is a modification of John's pixel driver. I love John's code. It's so readable. It's so helpful. I've really enjoyed going through and just looking at his code. My code is not good, just so you understand. You would never want to use any of my code as examples, especially with this project. This project was just done as a get through it as quickly as we can. So this is what the rig looks like set up and configured. I have two 30 amp power supplies that run the LEDs. Those LEDs get extremely bright. They can be seen in the daytime in the sunlight if you have it going 100%. You only need to have it run about 50% as a display at night for the Christmas stuff that I do. Here's where the outputs are all driven. One of the problems that I ran into early on, and I'm probably going to put a set of buffer chips out here for this, is you have to ensure that your ground goes directly to the ground on the power supplies for the pixels. And if you connect it just to one and you have them paralleled, that's not good enough because it will interfere with the data stream, and you'll get flashies and interference with the pixels. So you have to make sure that you have no ground loops for this to work properly. Let's see here. Here's what the overhead looks like of it. There's the WizNet board that I'm using. I'm not using SPI to pull the data out. It is a parallel bus. And so with the parallel bus, I assumed I could get data out faster. At this point, I'm not sure if that's true or not, just based on the fact that I had to put a lot of delays in there to be able to read good data out of it. I don't know if it's faster or not. So in the slide deck, here's my code. It's available. I have it out on visualstudio.com as a repo. I have links here for the Jinx matrix control. Here's where I got the module from WizNet. This is a specification from ESTA. The entertainment technology, I still don't know what the correct name of the association is anyways. That's where the E131 data packet specification comes from. Another good tool for being able to do light controls called Vixen Lights, which is a free piece of software. And of course, all of this is built around the wonderful Parallax P2 developer bundle, which I love that board. Let me show you guys some pictures of what it looks like when it's actually running here. Let's see here. So here is a video of it running 1200 pixels. And I don't know what the frame rate looks like coming across Zoom, but it's extremely fluid. I just could not believe how well it performed.
Yeah, Terry, it doesn't show nearly as well as the video I've seen over Zoom. So could you grab that YouTube link and drop it in chat?
Absolutely, I can do that.
It's too good to not see the right way.
Yeah. Okay. Yeah, so this right here is just a couple of different effects that you can do inside of Jinx. And all I did is sit there and flip through the different ones that are available and did this, sort of real time as a drop down. And it, it's really nice to have a piece of software that can sit there and generate all of this data for you so that you can kind of focus on what you want to do with it rather than spending a lot of time trying to figure out how to build the data structures to put into a microcontroller to display all of this stuff. And I don't know if this next video will show up good or if the audio will show up good. This is something that Jinx will allow you to do where you can capture a part of your screen and display it. And this is the opening sequence to Star Trek The Next Generation. I don't know what this is going to look like across the Zoom.
Hey, Terry, if you make that a little bit smaller, it might update a lot more smoothly.
Okay, let's see.
Yeah, that's faster now.
So obviously not a high definition display. It's only 1200 pixels, but it's just extremely fluid, and I'm certain there's plenty of optimization that can be done. Programming is not what I do for a living or anything. But to me, it's just a lot of fun to play with this stuff, and playing with the P2's just been a marvel to work with, and all of the friendly stuff, especially once you start getting into the assembly stuff. It's just been great. It's just been a real hoot. One quick thing I want to show is my yard full of P1s. And so this is about 2 acres of lights that I have through here. These arches are 11 feet wide. To give you an idea, there's the pixel display. This is 900 feet of fence right here that's lit up with multiple colors. And all of it's driven by P1s. So this coming up Christmas, everything is going to be ran by propellers, and that's going to make me very happy.
Wow. Living without a homeowner association. Love it.
That's on purpose. I have too many hobbies that are incompatible with that.
Terry, quick question.
Sure.
What did you say your frame rate was for transiting the DMX universes? How fast is it coming across?
So I don't know how fast I can go. I've been doing it at 25 Hertz. So it updates that entire display at least 25 times a second.
What about just for the traffic across the WizNet controller? How fast are they? You said there are DMX pairs coming in with each cycle?
Yeah, so there are 12 of those that were coming in. So each frame, I can gather a frame of, 6 milliseconds with that display.
So 1200 at 6. The reason why I'm asking is what's in my head is the P2 cube would be a fun target for this.
Oh, yes.
145 DMX frames, DMX universes, if I calculate that correctly.
I'll have to think about that. How many pixels is that?
2K pixels per side, 6 sides. Okay, am I right? 64 square.
Yeah, I think I can get up to somewhere around probably around 12,000, I think. For some reason, that number is ringing a bell.
4K per side, I'm sorry. So 6 sides of 4K.
Yeah, we could probably do a few sides with it. I bet if we could get a higher performance chip, like the WizNet 5300, it will probably do it. It's definitely the WizNet that is the bottleneck there.
Okay.
It's definitely not the P2. I can tell you that right now.
Any questions for Terry on chat or live or whatever? We can have him back in the future.
Great. Well, I hope I didn't take up too much of your time. Thanks, guys.
It's well worth
Thanks,
it, Terry.
That's pretty
Yeah.
cool.
That's
Super
wonderful.
cool. Yeah,
Thanks.
thanks a lot for sharing.
Yeah.
All right. Well, let's go to TeamOz and reawaken them.
You can hear me okay?
Hey, Brian, got you good.
Yep, good. So basically, the setup I've got here is a ST microelectronics time of flight sensor. Those of you who want to know the part number, I don't know if you can see that number there. Is that clear?
Yep.
So VL53 L5CX. So basically it's a time of flight sensor that gives you an 8x8 grid of zones. So you're getting 64 measurements. It has a field of view of 45 degrees and a range, I believe it's 4 meters. So the sensor, it's quite small. You can see the little board. I don't know if you can see it where my finger is here. Small board. And what I've got set up on the little HDMI display is the actual readings that I'm getting from the sensor at the moment. And what I've done is I've colorized the background, so the measurements that are further away, you get a darker background, and anything that's close, you get a brighter background. My webcam's probably not showing the colors that good. And on the right-hand side of the display, the line graphs that you can see are the actual horizontal readings, just displayed in a line format. So the lines that are at the top of the screen are the measurements or the objects that it's hitting that are further away, and to the front, obviously, are the closer ones. So, for example, if I wave my finger in front of the sensor, you should be able to see the colors changing there, and it's taking the reading. Now, this is in 8x8 mode. You can get about 15 hertz sample rate. I don't know if you can see that okay. And on the right hand side, you can actually see the readings in a more visual side of things. So I'll put my hand in front of it. I'll get closer and it'll get brighter, and you can see the lines drop right away, and I'll pull my hand away. And so there's a whole lot of data that you can get out of this sensor. It'll give you reflectance values, and now sometimes you'll see a little spike happening where it's actually getting a misreading. And now there are status bytes that you can actually read that lets you know that the ranging calculation was in error. I didn't have time to hook all that in to make it ignore the last reading, but yeah, basically you have a field of view of 45 degrees and you're getting 64 readings at once. It does have a 4x4 mode, which you can go up to 60 hertz refresh rate on that. So if you want to drop off the number of zones or the resolution of the zones and get your refresh rate up higher, you can just drop down to the 4x4 mode. So the drivers that run this, ST Microelectronics have a C library, which has all the bits and pieces you need to get the sensor going. Sadly, their data sheet's a little bit vague on how the thing works when you want to get down to the nuts and bolts. But the library, if you start pulling that apart, you can sort of work out how some of it works. They seem to be a little bit secretive on telling you too much about it, but it has an I2C bus. So you can collect the data that way. So I'm basically running the C library. I'm running PASM code to run the HDMI display. And I've actually got some spin code that's actually talking to the C code to make the HDMI display work. I'm not a C programmer, so I had a bit of help from Rog Lowe, who's the C guy. And so this has been compiled under Eric Smith's FlexProp. And yeah, it's this is only early days of playing with it, but it seems to have a lot of potential, I think, for robotics, for vision systems, where you maybe in combinations with video cameras with this data, you can actually measure where objects are in space.
Hey, Brian.
Yeah,
So this thing actually returns 64 measurements per cycle,
that's right.
and you can have it be one-dimensional 16, or you can have it two-dimensional 4x4.
It's still two-dimensional 4x4. It's just to get the frame rate up. They obviously just drop off their sampling. There's an MCU that's on board that when you first initialize the thing, it loads about 85K of firmware into it, and it's doing all the hard work. And yeah, it's just basically streaming out the 64 measurements.
So, okay, so that thing, how is it resolving? I understand time of flight, but how does it get spatiality? Does it have like different transmitters pointed in different directions, or
as far as I understand it, it's got a fancy lens on built into the front of it. Yeah, the data sheet doesn't really go into it in great detail, but yeah, basically it's sending out or measuring 64 zones.
wait,
yeah,
it's sending out 64 what?
It's measuring 64 zones, and my understanding is it's through a special lens that it's got. So, but
There's no moving parts, right?
No moving parts. No, but I believe there's 64 receivers in it.
There's a picture of the chip in a link I just put in chat,
Oh,
Okay.
if that'll help. It's from STI's site.
Yeah, it might be one of those Fresnel lenses, which kind of are flat, but for multiple sensors, it might be sense to use them.
That's fascinating.
But it's a very tiny device. Now this board I'm using is I think they call it a satellite board. It's SD Electronics have their own sort of standard little evaluation boards. I believe
They're linked at the bottom of the page.
Yeah, I believe it was about $15. I think that was US dollars. I'm not sure because Tubular actually got them in, so he paid the bill.
Mhm.
But yeah, I believe they're pretty cheap, but quite a small device.
That's a lot of sensing for $10 a DigiKey.
Yeah, there you go. Yeah.
It's amazing. They only have 10 in stock.
So straight away, obviously robotic type vision, maze solvers, that sort of thing, you could see that it'd be quite useful.
yeah, it says the reflection of this light is focused by the receiver lens onto a SPAD array.
Yeah.
So the array must be like, it says, let's see, up to 8x8 zones with 63 degrees.
Yeah.
Huh. It says, thanks to ST histogram patented algorithms, the VL53 blah blah is able to detect different objects within the field of view. The histogram also provides immunity to cover glass crosstalk beyond 60 centimeters. So this is that 85K of firmware that you said is in the device.
Yeah. Yeah.
Interesting.
No, your library loads that up when you start up. So when you first initialize it, there's a bit that goes on before you can actually start using it.
You're saying it takes some time to power up?
Yeah, once you start it up, it's probably 2 or 3 seconds while you're loading all the firmware in over I2C, and then off it goes. And that has to be done every time you power up.
Wow.
I see.
40 meters of range?
400 centimeters. So that'd be 4 meters.
4 meters,
Yeah, 4
sorry.
meters. Yeah.
So you could count people, objects, cookies, or whatever.
Yeah, quite possibly. But you also have to remember, because of the 45 degrees field of view, the further you go back, your spread comes into play. So you probably have to apply a bit of trig.
Mhm.
But yeah, you've got that data there. It's what you do with it is. So yeah, their library it just basically was just spitting out the measurement data just serially, and I've just turned that around and put it into a visual format just to play with. So there's only early days with playing with it, but I've got it to this point where I can sort of see what it's doing and try it out. But yeah, there's things for motion sensing, all that sort of thing. It's all there. Yeah, and it nice and easy. Once I got around the C library stuff, which, like I said before, I'm not a C guy, so I needed a bit of help there to get that working. But there was a few modifications that had to be done to the C code to let FlexProp deal with it. But yeah, I'll post that stuff once I've got it all a bit more stable. And yeah, it's good fun.
That's pretty neat.
Yeah. That's about all I can I can show on it, really.
So you have that, is that what's on the bottom of your P2 eval board with the lights blinking? Or is that-
No, it's off.
Oh no,
on the
that's the
side.
IO board.
Yeah, that little board there. Hang on, I'll see if I can flip it up so you can sort of see it.
Okay.
You can see that?
Yes. All right.
So that's the little board there.
Wow. And you're showing about what, 8 measurements on the graph?
Yeah.
Oh, and then you're like kind of heat mapping the
Yeah.
the whole array, which is 8 by 8, right?
Yeah. So you can see my finger.
Oh,
waving.
I see. Okay, got it. Okay, it's like a camera, like a
Yeah.
low-res camera.
Yeah.
Why don't the bottom ones ever go off though?
The reason for that is it's with a 45 degree, it's probably looking at the bottom of my bench. If I tilt it up a bit,
Oh yeah, there you go.
there you go.
Now your finger.
Yeah.
Boy, that's interesting.
Yeah.
I have to think about what to do with that.
That's fun.
Yeah. Yeah, it's a big list of things I'd like to play with
Yeah.
when time permits, but this was the starting point anyway, so.
And I mean, $15 is not that expensive. I'm
No.
impressed.
No,
I'm
that's
pretty impressed.
pretty good, I think.
Yeah.
Terry, you could use that on your LEDs to control some kind of panning or something.
Yeah. Yeah, there's all sorts of, probably even detecting whether objects are square to a camera as well, that not on an angle. Yeah, there's all sorts of applications.
Seems like figuring out how to manage the data would be the difficult part, right?
Yeah, there's another mode in it that's a reflectance mode, which that might be useful in some applications. I haven't quite thought of anything yet, but yeah, it gives you a percentage of reflectance. So that might be useful in some conveyor applications with items going by that are potentially shiny or yeah, I suppose it's just combinations of what you want to do with the data.
Super. Any questions for Brian?
What's the little board that's on the bottom with the blinky lights? I can't quite make it out.
With the blinky lights.
Yeah.
Yeah, that's just one of the Parallax accessory boards. So it's got 4 LEDs on it and 4 buttons.
Ah, okay.
Yeah.
All right. Now
Yeah.
now I can see what you're talking about. I'm looking at it going, what is that?
Yeah, yeah. That's probably the most used accessory I think I use is buttons and LEDs. Yeah. Yeah, this board, it's pretty much almost 24 hours a day being used for something.
Well, great. Thanks for sharing this, Brian.
No problem.
We're looking forward to your winter because you'll be more available for us.
Sure.
All right. Well, let's see. Before we move on to motors, so it's cool. We've had lights, motion, now we get motors. Just want to share briefly, I think this screen. Just so y'all know, if you're looking for P2 edges, we are running out now. We were faced with a power supply chip shortage with a replenishment date somewhere in 2023. If you can imagine that. And when this stuff happens, it's just chaos because we have other things in progress. So like PC boards coming in, manufacturing setup, and suddenly we're not unable to build, but we're throwing away circuit boards, which is why you're probably getting keychains in your mystery boxes today that look like this, but without all the components that are just the PCB. But anyway, to our community, there are 30 more of these P2 edges in stock, and I think it'll be May, June before we have them back. So Michael has redesigned the power supply using a new chip, I think from TI chip. Is that right?
Yes.
Same rating, and we did both the P2 and the P2 edge, and we're just finishing the circuit board layout now. So it's all been proven out, and we're just going to go straight to production, but it's going to be, I'd say, at least 2 months. So you know. Sorry about that. We hate it more than you do, I assure you. Okay, so we have a video from Stephen to show. Just so everyone's up to speed on what we're doing with this. So Chip's been working with the BLDC, the brushless motor, the hoverboard motors for quite some time. And then we made the motor driver board, and Michael, Chip, and Doug did that, worked on that for a long time. We started it well over a year ago. And it's not perfect. We need to make some improvements to it, but we can run it reliably up to certain voltages, 18 volts with the hoverboard motors, and move things pretty darn fast. So Stephen took Chip's work, and he's made, extended it to have a top layer and all the useful control that I was begging for. And he's making really good progress. So we're going to see a video of that. And as you're looking at right now, this is some kind of round robot platform that he rigged up and ordered from Sencut Sen. And I'm going to get one of these too soon. And at some point, we'll be able to have the P2 as a nice robot controller with his driver on chips. And then even better yet, for the community much larger than Parallax, we'll eventually have a serial interface. So they'll be able to control these motors. And to my knowledge, there's not a good mid-sized robot controller available out there at all beyond what's in the hoverboard sphere. So this will be an application for people to do cool stuff with. So Stephen, what do you want to say about this? You've been working with it.
You did really well. Timeliness. You are seeing in the video what just happened for the very first time today. The Fly Sky control just started working today. And so let's watch the video and then I'll talk about it a little after.
Awesome. Okay. Let's do first. Is there sound here? I haven't watched it.
Well, okay. So
There you
what
go.
am I doing?
All right. Sound is good. All right. We'll carry on then. Enjoy.
You can recognize the Fly Sky control, and that's wired up. And this is a little bit of a RC demo, radio control demo, of my test platform, wherein I'm running code and talking to, powered by bench power supply, this guy. So this is my two-wheel test platform, and you can see that normally I'd have the battery hooked up, but I have the bench power supply hooked up instead at this point. This is nothing more than power distribution, fuses, 5-volt supply so I can actually drive the P2 plus a Raspberry Pi, and then the FlySky controller. And what you can see here is I had to run an extra 5-volt line for the FlySky controller so we could play with that. But that's pretty much what we have. That's our two-wheel platform. Okay, so now I'm going to be using this. I can't keep it in frame, but I can show you that I'm driving the motors. You can hear them being driven. You can hear that the ramping up
The frame rate's a little slow here.
not quite what I want it to be right now. There's too much torque. That's the noise you're hearing when I slow down. So I've got some improvement to make on the internal ramps. There will be likely external control of the ramps, but the internal ones right now could be improved. So you can see it jumping around. There's a lot of torque here. Now I also have steering in here. So hard right, hard left, right? And then I can just gradually let go of the yoke, and you see the other wheel go. There's my steering control so far. So you can see it's pretty responsive already. Whoa, hello. Somebody's running away. Yeah, we got to get rid of that kicking. I've not really added any control margin to the zero stop point. It's just, I just dialed in using these adjusters, the zeros. And so zero is stopped. So I just want you to hear that as well. Yep, it doesn't, it will stop quickly, and that's a really bad thing for these motors because it'll fault and then just shut itself off. So that's why we're putting in the ramps. Okay, that's all I have for now.
Looks good.
Okay, so now let's, as a last thing we'll do here in this demo is we'll take a look at the material you're going to find at the website with the motor controller. I don't know if I've shown you this. You might have seen part of this before. Here is the drawing files for my platform. This is the platform I'm actually using. These are little standoffs for the motors. So the casters are higher than the wheel motors themselves. They're little 1/4-inch things made out of the same thing. This is, I did this out of 1/4-inch MDF, as you can see here. Okay, so what are we looking at here? Single and two-wheeled motor control objects for the BLDC motors. Let's take a look at the interfaces. And so we have a steering object, provides steering for both wheels. And the steering object here is drive with power and direction, where direction distributes the power to the wheels. This is the maximum power of the fastest wheel, I think, is how that's going to work. I'm just putting in that. That's what you see me driving with FlySky right now, is I'm driving power and direction with the 2 joysticks. And you can see that it's just -100 to +100 for both fields. Drive for distance. This code is all in there and working. There are more distance units than this. I got to update the dock. Drive at power, where you can control each of the wheels independently. Stop after rotation. So you say I want to drive, you can stop after a distance through rotation or a distance in distance units. And you can stop after time. And so basically you said, let's say drive 50% power both wheels. It's going to go straight ahead. And you say stop after 2 feet or something like that. You can actually ask it to do that. Pretty easy. Starting assigning the base pins for the pin groups for the cards. Stop. Set acceleration speed, max speed for distance. This allows you to do braking or just turn off the power at the end of a travel when you say stop. This is reset tracking. It tracks in distance. You can reset it, and then you can see how far the hull sensors have indicated you moved. And so that's what we currently have, get power and get status. So this is the last power you assigned to each motor. Same thing with status. Is the wheel stopped? Is it moving? Are we running to go somewhere? That kind of thing. Then you have the motor itself, which has a very similar interface, but now you're talking just about one motor. The steering object you have right here controls the motors as a pair. And so you get that's why you get direction involved. If you had just a single motor control, then they've got similar interfaces. So drive, spin the single motor for distance, drive at power, stop after rotation, stop after distance, stop after time. That's all here. Same thing with start. We don't know if we're going to be using calibrate yet. There's your reset tracking, and there's your get information. And that's pretty much the new interface for the motors. I just wanted you to make sure you knew that this kind of documentation is going to be available. This is also in as dot comments within the code itself when you get the spin code. So that's what I have for the motor drive. Let's see if I can show you one more thing. There are also drawings of how I anticipated if you're using with the different boards. So here's the edge mini, like the arrangement I have. I suggested I could put 2 batteries down below if I wanted to. Johnny Mac board, where it would be located on that little tiny platform, that's a 17.5-inch platform. And then I had suggested a square platform as well, and I don't have the diagrams in here for the new wheel enclosing platform. But you get an idea of dimensions that I used. 25 by 16 if you wanted a rectangular. All I did was make sure the wheels were balanced in that case of the single caster. So just various resources that was 2 scale drawings at the website. All right. Thank you for watching.
Yeah, looks super. Hey, have you thought much about the math to coordinate the simultaneous wheel movements to integrate position and like X, Y, and heading?
I have not, but that's coming because we have a single cog monitoring the Hall sensors from both motors simultaneously. It's sampling 8 times a second. And so sampling much faster than that was a little bit more problematic than you might imagine. You have to let some time distance go by for the Hall sensors. Hall sensors are at what, 4 degree increments?
Yeah,
90
yeah.
per rotation. And so you have to let some time go by to have some sense capability.
Well, you know,
So,
you could make it, I could help you if you want. We could put that down in the assembly driver so that we could integrate upon change, you know, because I was kind of thinking about how that math's going to work. And you can't let too much time go by before integrating. Otherwise you can wind up with these big cumulative errors. You have to make it as tight as possible. And really, we could integrate off of the actual angles, never mind what the Hall effect sensor does, because if the Hall effect sensor ever gets too out of phase with our control signals, then we have a fault condition.
right.
So we could just integrate off of the, right off of the angle that we're giving the motor. And then we get super accuracy. Because I think if we use 4 degree steps, it's gonna wind up having a lot of cumulative error.
Yeah, that's potentially true. Let's I'm working to get this out into people's hands first, and then let's work on accuracy and tracking like that. See what we can do. Right now, we'll be using the driver as is. We'll use 3 cogs, one for each motor, and then one for the sense tracking of both motors. There's room for us to be able to move all of that into a single cog, actually, probably.
Yeah.
Not be too problematic. So we have life could get a lot of fun with optimizations of this driver, but I think it would get a lot more fun when we have more people playing with it and coming up with ideas that are more experienced in robots about how to do this kind of stuff. And so I'm gonna get me out of the critical path initially, and then I'll be glad to incorporate changes back into the code base for redistribution to everybody as more people contribute. And so I'm setting up for that.
Yeah, that's a good plan. I'll put it out there and let people use it, and then we can add to it and probably get some other developers. And then for anybody that buys the motor controllers too, if you may find, hopefully you won't, that under certain conditions with higher power, or if you mess with some of the timing constants in our example code, you can blow up the boards. So in the future, we're making a revision to that after we get the P2 Edge and the P2 Edge 32 megabyte out of the way. So if you get boards from us and you start using them and blow them up, that's totally fine. I'll replace them for you, no charge. We have 170 in stock, but just realize when these get low, I can't replace them with the same kind, which you wouldn't want anyway, but you would get the new ones. So you're part of the development process a little bit.
Also, a note, Ken, if
yeah.
I may, I've been running with a cheapy lab bench supply, but what that allowed me to do is give you controls built in and limits built into the driver, such that if you're running S2 through S5 batteries, the driver will know about it and do the right thing with scaling power and everything else. So you'd be keeping away from faulting and from harming the boards, hopefully, as long as you run it with constants. So when you actually first start up the code, you're providing the base pin for each of the boards and the voltage for your power system. And it'll set up all the internal constants correctly.
The problem with that motor board that we've had is that these high side, low side driver chips, which allow you to use 2 end devices, have this thing, a pin, they seem to be always called RS, and it's the feedback pin from the center tap between the 2 FETs. And it needs to come in at very low impedance because it charges up this flying capacitor, which is used to switch on the high side end FET. So we really can't put more than 3 ohms resistance in there without affecting timing badly. But what happens is when you have a big motor like these hoverboard motors, they have a lot of EMF kickback because you've got big inductors you're charging up, and when they let go, they send out big current pulses. Like, and in this case, the high pulses aren't the problem, but it's the negative pulses. It's hard for us to stop them from going very far below ground through a 3 ohm resistor. So we have the 3 ohm resistor, then we have a decent diode, but it still lets the voltage get negative enough. The diode goes to ground, right? So that if that resistor gets too low, it clamps to ground. But the trouble is the diode won't stop it from getting to like 1.4 volts or so. And that's enough to send the motor driver chip in, or the FET driver into latch up, and then it self-destructs. But if you're dealing with, motors like this that aren't that big, I think that's what that chip was designed for. No problem. These don't make very lethal EMF like the hoverboard motor does. So we're redesigning that board to use a Texas Instrument part, which can tolerate minus 21 volts on the RS pin. So that's more than we ever see. The most we ever see is like 4 to 6 volts. And so that'll be safe. So that chip was designed with bigger motors in mind. But what the board we have now, it's perfect for stuff like this. But these big inductive hoverboard motors can wreck the board if you get a big pulse. And Steven's been working with playing around with like the dead time between switched on to switch off, trying to minimize the problem, but it's kind of difficult. We can't guarantee it's not going to wreck it.
And when we get that redesign done, Chip, and we still have these, they'll wind up in a mystery box. in pairs.
Right on. Well, it's fine for small motors. It works great.
Cool. Well, Stephen, this is fantastic. It's great to see it happening now. So good job to you and Chip.
Oh, thank you.
Yeah, you know, this trig thing, Stephen, I keep trying to think about it, but I can't get anywhere. One or both of us will have to, at some point, work it out. I know the solution is not going to be that complex once we get it. It's just, it's one of those hard things to figure out. It's going to take like some dedication, but then once we think hard enough about it, it probably won't take more than an hour to work out.
That's probably true.
Okay, so Chip, I have to drop to go to my meeting. So I'll sign off and you have control.
Okay,
And the recording continues till you stop it.
right on. Okay.
Okay, thanks everybody.
Thanks, Kent.
Bet.
Again, good seeing you.
Too.
All right, I'll show you guys. I've been working on this debugger, and OzProp dev Dennis here. When we were making the FPGA Verilog stuff, he like really ringed out the all the single step stuff so that it works nicely. And he's made a little command line debugger, but I've been working on kind of a graphical version. So let me show you. Let me share a screen here. Let's see. There we are. Here's some code. So let me make this a little smaller. Anyway, so here is some code, right? This is spin code, and I have some inline assembly. So I'm just doing some stuff here to create some stuff to look at, and then here I do a debug. And this is a new command, break. So when I run this, let me drag this thing down. This is just kind of my little test bed here. It's not at all final, but I'm having to work out how to display stuff, you know, so it's compact and is going to work nicely. So when a debug breakpoint comes in, the PC receives a 16 long packet, which has like a bunch of status information, like the I return. It's kind of filtered from the debug. See, here's the debug. I'm eventually going to get rid of this thing that it won't even say cog 0. It'll look like nothing came across the main debug system. So this is all kind of stealth and uses packets which have, you know, initial low values to tell the system, okay, we got a debug, so disengage from normal debug stuff. But anyway, if you look here, you can see that you can see the count, the 64-bit counter running. And what's happening is I put in the debug thing that when a debug interrupt occurs, the likely thing the PC is going to want to do, because it has to display the information, and then it has to get some kind of input from the user, like a button press, like, okay, single step or jog or resume full speed. So before you have that, you can just tell the cog, hey, I don't have anything yet, go back to what you're doing. And then he calls back in 64 milliseconds. So we just give him this pause thing, and then he alerts us again with a whole new message. So as these new messages come in, you can see, can you see my mouse cursor? Okay, these are the count values here. Here's like count low, count high up here. So it just resends the current packet without having stepped anything. And that way, this thing can just kind of, you can run normal debug messages between this thing spitting out its hey, what have you got for me? Or have you got a button press yet? So in the background, you can run all your normal debug displays. You can run up to, you know, all 8 of these things, and they all play together without anyone, you know, pulling the rug out from anyone else. So I have here, we hit a breakpoint, right? If you look at our code, Let's see if we can show both. So here is this stall eye. I turned interrupts off. You can see that indicated down here. And again, this has to kind of finalize and take better form, but I did a thing to set up event SE1 for int1. So if you look here, int1 says it's configured to SE1 and it's waiting right now, meaning it's generated an interrupt, but because we have interrupts blocked, it can't do anything. So this is still running main code right here. This is our main code. And when it does the debug break, it shows as the first thing the instruction right after the break. So I'm going to have this thing so it'll show you the actual line you're on. Right now, I'm just showing what's going to get skipped. But you can see that right after the debug break, there was an add 0, 1, which is this right here. And that's at register 6, register address 6. And then we have a, let's see, where's that? Test BN, a test PN. And then because up here on the skip, we told it to go 4 instructions and then skip 4. You can see that we have 4 shaded out because those are going to get skipped. So I still have to do a lot of stuff with, you know, where the execution line is and making it so it can move a little bit and scroll the screen, but not be always super rigid. And then I put some no ops after it. I did this thing here, this if NC and not Z. That's like the most obnoxious, potentially long set of operands of any instruction decode or disassembly you could do. So I had to make sure I had enough columns here to accommodate the if NC and not Z. That's the longest condition. And then what I did, because that situation is so exceptional, and this is the next most exceptional right here, this read long. So I accommodated the next most exceptional situation. There's always room for that, but this one will just get truncated, you know, because we have to make some kind of compromise. Otherwise, we have lots of wasted columns. And here's the write fast pointer. Someone like OzProp Dev who knows how this write fast works. Although Stephen, you might too. You probably do. Brian, what do you think this represents here? Is this clear what does this line mean that says write fast? Is it intuitive?
Yeah, that's showing the internal pointer for the FIFO reads. Is that right? Or writes?
Yeah, so it means that you have read fast versus write fast, right?
Yeah.
You're always in one or the other because the FIFO is always alive, but it may not have to do anything. But so this says you're in write fast mode. And what's the 100 mean to you?
That's the current address.
Right. And then what does the F7 that's highlighted mean?
I think about that.
In other words, see, there's like how many? 1, 2, 3, 6. There's 13 bytes shown here, right?
Yeah.
And then the middle one, the very center one, is highlighted.
Oh, right.
So what must that be? What address do you think that one's at?
That would be the end of the FIFO, is it? So, or is that the next? Hang on.
Well, it would be the 100 address. So this is the first F7 that's not highlighted. That would be location FF. The CB would be location FE. Because I figured,
oh yeah,
you have to show, you know, the write fast, read fast, depending on what mode you're in. If you're in write fast, the data before the current pointer is where you've been depositing data. And if you're in read fast, the pointer is going to say what you're going to read next.
Yeah.
Right. So we just show like, you know, 6 bytes in front of and in back of the current byte.
Yeah. Yeah. Yeah, that's useful. Yeah.
Okay. So there's a lot of stuff, some things like that it's not fully explained, but it's one of these things where as soon as you start to use it, it should be like pretty apparent. Because this thing could get really verbose if I let it. I want to keep it kind of like an instrument, you know?
Yeah.
And then the int 1, int 2, int 3, it tells you if you have a source selected and then what the status is. That could be wait, idle, or busy. And then if it's off, that means there's nothing. It's just set to 0. There's no interrupt source for int2 and int3 right now. Like if I go here and I say, let's set that to event SE2, then there, now it's SE2 and SE2 is idle. So no interrupt is waiting. And then this up here shows you if you're in main code, ISR1, ISR2, or ISR3. And then here's the Z, PC, and whether you're in reg, LUT, or hub, right? Depending on the address range.
Yep.
And then I've got, just when we were on the meeting, I added this little bit in down here so that if I touch like the bottom pins on my breakout board, I can make these changes. I'm going to put something in there so I'll highlight or inverse the digits that are changing from cycle to cycle. So I'll have some kind of like record of what the whole data was last time so that I can highlight any changed digits, you know, from cycle to cycle. So you can see where the action is.
Yeah.
And I've just got to add over here, I've got some, here's kind of my plan for this. Let me see here. Let me make this a little bit smaller. Yeah, so I've got to add buttons to show what you want to break on. Do you want to break on just main code or interrupt entry code, interrupt execution code, or a certain address, or you want to break on an event, or this is always enabled. This is what debug uses. This is what gets you into the debugger. And then I've got to make some watch windows that need some kind of specification. And then the buttons that I got to add are just these: go and stop, go and animate, stop when animating. That's pretty, not very complicated, but it will get you into assembly language and watch you track everything that's happening.
Nice.
Yeah, this is nice.
So, you know, when you're running what I don't have, and I don't have any immediate plan for, is symbolic debugging at this level, because there's a lot of ambiguity, because we have self-modifying code everywhere. You know, any crazy thing could be going on. And it's really, if you try to work out the problem of, well, what cog is running what code, you really don't know at compile time. So you can't make any kind of determination about, oh, that's cog such and such. You'd almost have to apply some kind of like AI to figure out, okay, it looks like he's got this code in the cog right now, but then it's not certain. So this is at least going to be just good for, you know, single stepping in assembly language and watching code. So if you wrote this code that's in this window here, you're going to know how it works, right? Or how it's supposed to work. So you'll be able to do that. And if you do a debug in a spin program, well, you're going to be looking at the interpreter executing stuff, and you're going to see the spin bytecodes down here, you know, as they get picked up and utilized. But it's just very low level assembly language debugging.
Very nice.
Any questions about this?
Yeah, one thing I had in mind, Chip, was where you've got the write fast showing what it's coming up or what you're going to read. I had a similar thing with the stack. If you're using pointer A or pointer B as for a stack, you could actually look at the values that you've actually.
Oh, yeah, like call A, call B, return A, return B, that kind of thing.
Yeah, so you could actually see what you've just pushed onto the stack.
Yes.
What your hub stack contents are, you know?
Yeah, okay, I'm going to add that to my little thing here. So we need like just a couple values, maybe like 5 values for each or something.
Yeah.
Okay, so pointer A, pointer B longs.
Yeah.
Pointer 2. Yeah, and I need to make also some kind of, I mean, people are going to want to be able to, because they can in this thing, they want to be able to look at maybe a range of hub memory or register memory that's outside of the special registers. I need to come up with some way to trigger that and to specify, you know, what it is. And I could,
like a hex dump that's triggered.
yes.
Yeah.
Yeah, but I want to keep it. See, I'm going to, as I work through this, I want to take the most basic parts of this and I want to like compact it so that it's kind of set like an instrument panel, you know?
Yeah.
And then these watch windows need to be something that are flexible. I don't know if I need to make their size flexible. I'd like to constrain them to the same window just to keep it under control.
Yeah.
But I'm not, that I have yet to go there. That's like kind of like the big thing I'm not certain about yet. And I could make it so that, you know, you click on things and it takes those addresses and shows you more, or there's a lot that could be done.
Yeah, that'd be a great way to focus the area that you're dumping.
Yeah.
Mhm.
Yeah.
Maybe you could just have a few buttons that just change what the contents are in that large window.
Wait, right. Yep.
So if it was a
Yeah.
hex dump, you could just hit the dump button or something like that and it swaps what's in that large screen. So
Yeah,
it's
that's
multi-purpose.
That'd be
yes.
good reuse, yeah.
Yeah, and I could have maybe a couple of windows. I mean, I think the disassembly should remain, but I could have a few little windows below that are just set, which can be, you can select, you want to look at, you know, cog, LUT, or hub.
Yeah.
And then have some mains to kind of scroll around in there. And also when you come into the debugger, from the break thing here, I could overload this thing so that you could add stuff about, you know, show me starting at this address.
Yeah.
Sure.
And then if you put a symbolic name in there, well, it would show you, the first thing it would show would be the variable that, you know, you were pointing to.
Yeah.
So yeah, that's something that needs some evolution.
So provide a little bit of context, Chip. What did you put in your code to make this display show up?
Right now, just this, just debug break.
Oh, nice.
So wherever you are, boom, it goes into the debugger and it shows you some stuff. But we can add to the break, we could put some like watch syntax in there so that when it goes in, it's pointing to something of interest to you.
Gotcha. In addition to current context. Yeah.
Right.
Very nice. Very nice.
Yeah, and the key is going to be just keeping it not too complicated, you know, keeping it simple. And I'll probably build the buttons just by looking, like tracking the mouse movement and checking where I'm at on the screen.
Mm-hmm.
And that will, then I can kind of do anything I want without getting into the way Windows forces the interpretation of everything.
Yeah,
so you can have multiple breakpoints and maybe a button for like next breakpoint.
Yes. Here, I'll show you. Let me pull this in here. These are the buttons that I need. And then buttons that say, you know, go and stop, go and animate, like single step, animate, or stop animating. Let's see.
Animate is just continuous run at the slow rate.
Yeah, and then just run. You know, just take off until you need to come back. So this is, I should call this, let's see, single step.
There you go.
And then multi-step, like animate steps.
Yeah, it'd be nice to have animation at a certain rate, either slow or a little bit faster, you know, so it's adjustable, the rate.
Yeah,
That's
okay,
possible.
okay. Add rate control. Okay. And that's something that could be like, we could do a default and then have it overridable when you do the debug.
Yeah.
Right.
Or even by some kind of, well, yeah, maybe when we do the debug, because you want to have different setups for different cogs. We don't want just one overall like global label to define something like that, I guess. So we can call that out, add rate control via debug statement. I'd like to make it so that if possible, I don't get into all kinds of little menuing and data entry things on the debug display. Because it's important to be able to specify, but it's maybe more it's really nice to be able to specify at compile time in your code what you want to have happen.
So when you have a break in a cog, it'll bring out that debug screen, and then you could go to the next breakpoint in the same cog, or there might be another break in a different cog. You'll know what debug screen you're on by the cog 0, cog 1, cog 2, right?
Right. Yeah. Here, let's see. And I'm thinking that, okay, I'm thinking that I should probably put that in some big font down here. I don't know. It seems kind of weak to have it up there in the window header or in the frame. Maybe it's okay.
Or you could, yeah, you're gonna be wondering. You're gonna have to be looking at what cog just generated that breakpoint.
Right.
You know, if it's the same cog 0 because you got multiple breaks, or different cog generated a single break. You know.
Right.
That's going to be important to realize that in debug.
Yep.
I mean, plus when you have another breakpoint, will this window collapse when you leave that step?
Yeah. Well, once like a cogs debugger window is open, it stays open until it gets closed, either by hitting, this or hitting F12 to stop all debug stuff. And so anytime a new breakpoint comes in, this display just updates. You see these 16 longs here?
Yep.
That fully describes the context. Everything is there to key into everything else you need to know what's going on.
Mm-hmm.
So that's a packet that gets sent kind of under the radar through the debug system. And this whole thing works in real binary, not ASCII. So it's as efficient as can be. It's more efficient than normal debug stuff.
So this is a snapshot that occurred at the break in one cog. It'll remain there, and as another cog, since it's running, gets a breakpoint, another window will appear.
Yep.
Oh, okay.
We should try that. Let's see here. Let me go, let's say, let's see. How about we go like, let's see, I guess I could do a cog init from within inline assembly, right? Cog init, let's see, what's the first thing? It's the cog number, right? And then where it's at, this, maybe I need to do it. Maybe it'd be safer to do it out here. I've never tried it yet, but it should work. So if we say cognit 16 comma at program 2, or wait, and then there's another value we could give it, right? Is that all we need? That says new cog. I think that I could go like this. This is a constant. Wait a minute. New cog. Let's see. Does that even compile? Yeah, that's good. So down here, I'll say dat, and I'll say org, and then pgm2. This will just immediately do a debug break, and then how about or 1, 2, and then return. Okay, now let's see now. If I run this, yeah, so here's cog 1. Yeah, you see up there at the top, or 1, 2, and return. And then this is just whatever data was, following in memory, kind of in a turn. So this is cog 1, and then this is cog 0. So see, they're both working. And then the normal debug stuff can also happen in the background with other cogs, or even these cogs do a normal debug, like debug display type stuff.
This is nice.
It's funny, I never tried it, but it should work, and it does work. And that's good, because that means that, you know, the PC is having separate conversations with two different cogs, and they're getting back and saying, you know, telling them to take a break, come back later. They're each calling back later. So see, they have different things. Like the cog 1, the second cog doesn't have any interrupts configured. But if I touch the bottom pins here, if you look at NA, those are going to be the same, right? Because everybody sees the same thing. The stack values would have different stuff on them. Oh yeah, cog 1 had never done anything since reset, so all the flip-flops got cleared to 0. So and its read fast pointer is at 0. So now I got to see how that works. You know what? That needs to wrap around. I don't know if that wraps around properly, because that would be FF, FFF, FF, FFE, and so on. Anyway, yeah, so you can have 8 of these windows kind of just hanging around, and each is, you know, each will have buttons. You can tell each one to advance, and nobody's the wiser, you know, they all just do their own thing. No one's stepping on anyone's toes.
Yeah, that's nice.
Thanks. Yeah, this is a big thing. And OzProp Dev really got this thing worked out nicely. He went and made sure that I made it so that it single stepped properly. So once I get the interface all done, it should work really nicely. You know, you'll be able to single step, you'll be able to watch it skip instructions. And if you're in skip F mode for fast, it'll leap over instructions. If you're in normal skip mode or in hub, you'll see it just no op instructions that are that are actually being skipped.
Very nice.
So anyway, that's about that for the debug stuff. Okay, let me stop sharing here, and I'll stop the recording since that's kind of like the end of the